So let's move on to Cartesian product and join. Now, previously we've looked at two particular relational algebra operations. We've looked at projection, and if you remember what projection does is it actually chooses particular columns from a table or from a relation. Something like this. Let's imagine that we were particularly interested in emp number, ename, job and sal. Then a projection would enable us to gain those particular columns. So we did projection first, and then we had a look at selection, and selection enables us to choose particular rows. So for example, we might have a table, the emp table for example, and there might be particular rows that we wanted to see. And so we just have a condition of some kind that will allow the rows that we want to see to come through. So we've done projection, we've done selection. Now, the next obvious question is, we can take a table and we can cut it into rows, we can cut it into columns, but you may have noticed that in all the examples that we've looked at so far, we've only actually been working on one relation or one table. And so the question is, what happens if we need to collate or collect information or display information from more than one table? Now, we can do this by using an example. So let's have a look at this one here. It says, list all staff along with the location where they work. Now, so all the staff and where they work. Okay, so if we have a look at the particular tables that we have in this data set, we have the emp table, and if you scan across, that's obviously got people, how much they earn, when they're employed, and we've got department number on the far right hand side. And we have a different table called department, and that's the table that actually has the location inside it. So our query says, show me the people and where they work, and of course that means we're going to need these two tables combined together. Now, the way that we can do that is to use this operation called Cartesian product, and that's represented by a cross. And it means combine relations together. Now, here's the full definition of Cartesian product, and the way that we would write that down is we would write it like this: R cross S, and R and S are relations, tables if you like. And what we're going to do is we're going to combine those together. And here's the formal definition. As you can see, it says the Cartesian product operation defines a relation that is a concatenation of every tuple of relation R with every tuple of relation S. In other words, everything from this first table will be combined with everything from the second table. And that's exactly what we want. We want some way of combining tables together. So let's see how we would write that down. So we know it's going to be using this notation, R cross S, or X cross Y, or whatever letters you particularly want. So we want to combine emp with department, so we simply write that down and we go emp on that side and department on that side, just like that. And if there were more tables required, let's imagine you wanted to combine three tables, it would be A cross B cross C. Very similar the way that you would write down, a multiplication, for example, 3 times 4 times 7, something like that. Now, let's have a look at what happens if we actually try and do that. How many sort of results, how many rows would we get in our results set? How many tuples? So let's imagine that we could actually run this against the database in some way. This is what we would get back. Now, there's lots and lots of data here. So let's actually look at this quite closely. As you can see, it's not quite what we were expecting. We're trying to combine emp with department. We're trying to combine the emp relation with the department relation. And you can see that for some reason, when we put these two tables together, we've got multiple rows being repeated over and over again. So if you just look down the ename column, you can see March is repeated over and over again, burn, bell, bird, etc. And obviously I can't fit them all onto the screen here, but there's lots and lots of rows that aren't being displayed. And of course that's not really what we're looking for. we simply want to see people and where they work. And there's something going wrong here, because if you look at March, for example, if you scan across, then it's saying that March works in London, York, Birmingham, Leeds, similarly all the way down. So this operation is succeeding in combining those tables together, but for some reason we're getting lots of rows that aren't correct. So why? Why is that actually happening? Well, the clue is in the actual definition of Cartesian product. So if we go back to that, what it actually says is this. It says we're going to combine the tables together, but it's this bit here. It says every tuple from R is combined with every tuple from S. So in other words, every row is combined with every row. Everything in the first table is combined with everything in the second table. So if we have 14 rows in the first table and 4 rows in the second table, we're going to end up with 56 rows in our result set. And clearly, many of those are incorrectly matched rows. But that's what Cartesian product actually does. That's not wrong. Cartesian product is an operation that databases implement that basically combines tables by taking every row from the first table and combining it with every row from the second table. And this is one of the fundamental places where people go wrong if they're trying to move to databases from flat structures like spreadsheets. They start thinking about combining tables together, and they don't actually understand what databases do is they actually implement Cartesian product. This is where most people make mistakes in query when they're writing queries. They forget you will end up with masses and masses of data because every row will be combined with every row when you use more than one table. Now, let's have a look at this and see if we can find a way through to actually solve this problem. And what I'm going to do here is zoom in on 2 particular columns, have a look at the department number column. Now there's a key here that's basically going to show us how we can extend this and solve this problem. Obviously, everything from the first table is being combined with everything from the second table, and we're specifically talking about department numbers here. And you can see, if you scan across, obviously, this first person who's in department 2 has been combined with department 1, 2, 3 and 4. The second person who's in department 3 has been combined with 1, 2, 3, 4, etc. all the way down. So does this issue, does this column, these columns here, do they give us a way to actually find our way through to correctly combine the tables together? Well, in this instance, we have a column which occurs in both tables, department number. And if in some way we could keep the rows where the department number is the same, that would give us the correct result set. So when you're actually doing this, when you're going to be combining tables together, one of the easiest things to look for is the column the same in both tables? If it is, like here for example, we've got department number, we can use that to match on the particular rows. Because looking at this, what we really want to do is we want to keep the rows where the department number is the same. Now, just to mention here, by the way, that you'll notice there's a slight change in notation here. Clearly, department number is in the emp table and department number is in the department table. And that's a problem because when we combine these 2 tables together, we suddenly got 2 columns with the same name. And you may remember that we said inside a table or inside a relation, columns must have unique names. So this notation is used if we have duplicate columns. You can see what's actually happened here. Department number, well, we're going to call that emp.department number, the first one, and that's the department number that's come from the emp relation. The other one, department number, is going to be called department.department number, and that's come from the department relational table. And you'll see how we use the dot. So we have table name or relation, and then a dot, and then we have the particular column. So using that notation, what we really want to do is we want to keep only the rows where the match occurs. So in other words, only show me, only keep rows where emp.department number matches department.department number. And if you think about it, the way that we could do that is to use a selection. And we've done selections before. We've done things like, where department number equals 3 or where job equals manager. Well, here we could go where, and we could use that as a condition. Only keep the rows where those numbers match. So let's write this down in relational algebra. We'll start off with our Cartesian product. So we go emp cross department. So that combines everything from the emp table, the emp relation, with everything from the department table, the department relation. And what we're going to do is we're going to add a condition to the outside. Now, the way that we do that is to use a predicate like this. And we put our condition in, emp.department number equals department.department number. And what that will do then is, we do the bit in the brackets first, combine the two tables together, and then only keep the rows where the department number's the same. And if we run that, if we could run that, but we can do it sort of mathematically, we would get the correct set of results. So here you can see the two tables combined. The emp table is on the left, the department table is on the right, but we've only kept the rows where the department numbers match between those two department number columns. Now that is an example of a Cartesian product and a selection. And what this means is you will almost always be wanting to use a Cartesian product, but you must remember to do the selection. Otherwise your result set won't be correct. That combination of a Cartesian product and a selection is used so commonly that it has its own name, and it's called an inner join.